Aiming for correctness. With stateless services that only read data, it is not a big deal if something goes wrong. You can fix the bug and restart the service, and everything returns to normal. Stateful systems such as databases are not so simple. They are designed to remember things forever more or less. So if something goes wrong, the effects also potentially last forever, which means they require more careful thought. We want to build applications that are reliable and correct, i.e. programs whose semantics are well defined and understood, even in the face of various faults. For approximately 4 decades, the transaction properties of atomicity, isolation, and durability Chapter 7 have been the tools of choice for building correct applications. However, those foundations are weaker than they seem. Witness, for example, the confusion of weak isolation levels. See weak isolation levels on page 233. In some areas, transactions are being abandoned entirely and replaced with models that offer better performance and scalability, but much messier semantics. See, for example, leaderless replication on page 177. Consistency is often talked about, but poorly defined. See consistency on page 224 in Chapter 9. Some people assert that we should embrace weak consistency for the sake of better availability, while lacking a clear idea of what that actually means in practice. For a topic that is so important, our understanding and our engineering methods are surprisingly flaky. For example, it is very difficult to determine whether it is safe to run a particular application at a particular transaction isolation level or replication configuration. Often simple solutions appear to work correctly when concurrency is low and there are no faults, but turn out to have many subtle bugs in more demanding circumstances. For example, Kyle Kingsbury's Jepson experiments have highlighted the stark discrepancies between some products' claimed safety guarantees and their actual behavior in the presence of network problems and crashes. Even if infrastructure products like databases were free from problems, application code would still need to correctly use the features they provide, which is error-prone if the configuration is hard to understand, which is the case with weak isolation levels, quorum configurations, and so on. If your application can tolerate occasionally corrupting or losing data in unpredictable ways, life is a lot simpler, and you might be able to get away with simply crossing your fingers and hoping for the best. On the other hand, if you need stronger assurances of correctness, then serializability and atomic commit are established approaches, but they come at a cost. They typically only work in a single data center rolling out geographically distributed architectures, and they limit the scale and fault-tolerant properties you can achieve. While the traditional transaction approach is not going away, I also believe it is not the last word in making applications correct and resilient to faults. In this section, I will suggest some ways of thinking about correctness in the context of data flow architectures. The end-to-end argument for databases. Just because an application uses a data system that provides comparatively strong safety properties, such as serializable transactions, that does not mean the application is guaranteed to be free from data loss or corruption. For example, if an application has a bug that causes it to write incorrect data or delete data from a database, serializable transactions aren't going to save you. This example may seem frivolous, but it is worth taking seriously. Application bugs occur, and people make mistakes. I use this example in state, streams, and immutability on page 459 to argue in favor of immutable and depend-only data, because it is easier to recover from such mistakes if you remove the ability of faulty code to destroy good data. Although immutability is useful, it is not a cure-all by itself. Let's look at a more subtle example of data corruption that can occur. In fault tolerance on page 476 we encountered an idea called exactly once or effectively once semantics. If something goes wrong while processing a message, you can either give up, drop the message, i.e. incur data loss, or try again. If you try again, there is the risk that it actually succeeded the first time, but you just didn't find out about the success, and so the message ends up being processed twice. Processing twice is a form of data corruption. It is undesirable to charge a customer twice for the same service, billing them too much, or increment a counter twice, overstating some metric. In this context, exactly once means arranging the computation such that the final effect is the same as if no faults had occurred, even if the operation actually was retried due to some fault. We previously discussed a few approaches for achieving this goal. One of the most effective approaches is to make the operation idempotent. See idempotence on page 478, that is, to ensure that it has the same effect, no matter whether it is executed once or multiple times. However, Taking an operation that is not naturally idempotent and making it idempotent requires some effort and care. You may need to maintain some additional metadata such as the set of operation ID that have updated a value, and ensure fencing when failing over from one node to another. See the leader and the lock on page 301. Duplicate suppression. The same pattern of needing to suppress duplicates occurs in many other places besides stream processing. For example, TCP uses sequence numbers on packets to put them in the correct order at the recipient, and to determine whether any packets were lost or duplicated on the network. Any lost packets are retransmitted and any duplicates are removed by the TCP stack before it hands the data to an application. However, this duplicate suppression only works within the context of a single TCP connection. Imagine the TCP connection is a client's connection to a database, and it is currently executing the transaction in example 12-1. In many databases, a transaction is tied to a client connection. If the client sends several queries, the database knows that they belong to the same transaction because they are sent on the same TCP connection. If the client suffers a network interruption and connection timeout after sending the commit, but before hearing back from the database server, it does not know whether the transaction has been committed or aborted. Figure 8-1. Example 12-1. A non-idempotent transfer of money from one account to another. The client can reconnect to the database and retry the transaction, but now it is outside of the scope of TCP duplicate suppression. Since the transaction in example 12-1 is not idempotent, it could happen that $22 is transferred instead of the desired $11. Thus, even though example 12-1 is a standard example for transaction atomicity, it is actually not correct, and real banks do not work like this. Two-phase commit. See atomic commit and two-phase commit to PC on page 354. Protocols break the 1:1 mapping between a TCP connection and a transaction, since they must allow a transaction coordinator to reconnect to a database after a network fault and tell it whether to commit or abort an in-doubt transaction. Is this sufficient to ensure that the transaction will only be executed once? Unfortunately not. Even if we can suppress duplicate transactions between the database client and server, we still need to worry about the network between the end-user device and the application server. For example, if the end-user client is a web browser, it probably uses an HTTP POST request to submit an instruction to the server. Perhaps the user is on a weak cellular data connection, and they succeed in sending the post, but the signal becomes too weak before they are able to receive the response from the server. In this case, the user will probably be shown an error message, and they may retry manually. Web browsers warn, "Are you sure you want to submit this form again?" And the user says yes, because they wanted the operation to happen. The post/redirect/get pattern avoids this warning message in normal operation, but it doesn't help if the post request times out. From the web server's point of view, the retry is a separate request, and from the database's point of view, it is a separate transaction. The usual deduplication mechanisms don't help. Operation identifiers. To make the operation idempotent through several hops of network communication, it is not sufficient to rely just on a transaction mechanism provided by a database. You need to consider the end-to-end flow of the request. For example, you could generate a unique identifier for an operation such as a UUID and include it as a hidden form field in the client application, or calculate a hash of all the relevant form fields to derive the operation ID. If the web browser submits the post request twice, the two requests will have the same operation ID. You can then pass that operation ID all the way through to the database and check that you only ever execute one operation with a given ID, as shown in example 12-2. Example 12-2. Suppressing duplicate requests using a unique ID. Example 12-2 relies on a uniqueness constraint on the request ID column. If a transaction attempts to insert an ID that already exists, the insert fails and the transaction is aborted, preventing it from taking effect twice. Relational databases can generally maintain a uniqueness constraint correctly, even at weak isolation levels, whereas an application-level check-then insert may fail under non-serializable isolation, as discussed in Write Skew and Phantoms on page 246. Besides suppressing duplicate requests, the requests table in example 12-2 acts as a kind of event log, hinting in the direction of event sourcing. See event sourcing on page 457. The updates to the account balances don't actually have to happen in the same transaction as the insertion of the event, since they are redundant and could be derived from the request event in a downstream consumer as long as the event is processed exactly once, which can again be enforced using the request ID. This scenario of suppressing duplicate transactions is just one example of a more general principle called the end-to-end argument, which was articulated by Salzer, Reed, and Clark in 1984. The function in question can completely and correctly be implemented only with the knowledge and help of the application standing at the endpoints of the communication system. Therefore, providing that questioned function as a feature of the communication system itself is not possible. Sometimes an incomplete version of the function provided by the communication system may be useful as a performance enhancement. In our example, the function in question was duplicate suppression. We saw that TCP suppresses duplicate packets at the TCP connection level, and some stream processors provide so-called exactly one semantics at the message processing level, but that is not enough to prevent a user from submitting a duplicate request if the first one times out by themselves. TCP, database transactions, and stream processors cannot entirely rule out these duplicates. Solving the problem requires an end-to-end solution, a transaction identifier that is passed all the way from the end-user client to the database. The end-to-end argument also applies to checking the integrity of data. Checksums built into Ethernet, TCP, and TLS can detect corruption of packets in the network, but they cannot detect corruption due to bugs in the software at the sending and receiving ends of the network connection, or corruption on the disks where the data is stored. If you want to catch all possible sources of data corruption, you also need end-to-end checksums. A similar argument applies with encryption. The password on your home Wi-Fi network protects against people snooping your Wi-Fi traffic, but not against attackers elsewhere on the internet. TLS/SSL between your client and the server protects against network attackers, but not against compromises of the server. Only end-to-end encryption and authentication can protect against all of these things. Although the low-level features TCP duplicate suppression, Ethernet checksums, Wi-Fi encryption cannot provide the desired end-to-end features by themselves, they are still useful, since they reduce the probability of problems at the higher levels. For example, HTTP requests would often get mangled if we didn't have TCP putting the packets back in the right order. We just need to remember that the low-level reliability features are not, by themselves, sufficient to ensure end-to-end correctness. Applying end-to-end thinking in data systems, this brings me back to my original thesis. Just because an application uses a data system that provides comparatively strong safety properties, such as serializable transactions, that does not mean the application is guaranteed to be free from data loss or corruption. The application itself needs to take end-to-end measures, such as duplicate suppression, as well. That is a shame, because fault tolerance mechanisms are hard to get right. Low-level reliability mechanisms, such as those in TCP, work quite well, and so the remaining higher-level faults occur fairly rarely. It would be really nice to wrap up the remaining high-level fault tolerance machinery in an abstraction, so that application code needn't worry about it, but I fear that we have not yet found the right abstraction. Transactions have long been seen as a good abstraction, and I do believe that they are useful. As discussed in the introduction to Chapter 7, they take a wide range of possible issues: concurrent writes, constraint violations, crashes, network interruptions, disk failures, and collapse them down to two possible outcomes: commit or abort. That is a huge simplification of the programming model, but I fear that it is not enough. Transactions are expensive, especially when they involve heterogeneous storage technologies. See distributed transactions in practice on page 360. When we refuse to use distributed transactions because they are too expensive, we end up having to re-implement fault tolerance mechanisms in application code. As numerous examples throughout this book have shown, reasoning about concurrency and partial failure is difficult and counterintuitive, and so I suspect that most application-level mechanisms do not work correctly. The consequence is lost or corrupted data. For these reasons, I think it is worth exploring fault tolerance abstractions that make it easy to provide application-specific end-to-end correctness properties, but also maintain good performance and good operational characteristics in a large-scale distributed environment.